So first, I'll discuss a bit machine learning field in general, just a few words. Then I'll go and discuss components of machine learning, the same topics that you had in the first notebook. And then just a bit about Python coding and Python classes. So let's start first and talk about machine learning field in general. I believe that even if you are not studying computer science or working in a field that is related to math or computer science, you heard such terms as machine learning, deep learning, artificial intelligence, statistics, data science, statistical learning, data mining. So a lot of these fancy words. And sometimes it's confusing how these fields are related and what are the methods and topics in each of them. So here an illustrations from some random paper that I found on the internet, where authors depict this relation in this diagram, and where all the fields are overlapping, and data science and machine learning, for example, somewhere in the middle of this overlapping field. Of course, this is a very subjective classification or representation of these domains, and you can depict it in a different way. But the point is here that there is no clear cut in dividing these domains in these fields. And many of these methods use the same methods. Many of these fields use the same methods, the same theory, and dependent on each other. So even though maybe statistics and statistical learning sounds a bit boring, then artificial intelligence or deep learning, in reality, it's interesting and important and exciting in the same way as many other words, like more popular in the public. Very often, the relation between artificial intelligence, machine learning, and deep learning represented as a nested structure. And deep learning is represented as a subfield of machine learning, and mainly deals with artificial neural networks and all of the models of the similar structures. Then machine learning usually something that deals with the algorithm and machines that improve with some experience. And then artificial intelligence is something high level. So those are like the final goal is to create the machines that would be that would mimic the human cognitive abilities or human behavior. And I sort of randomly selected a few definitions of machine learning from different sources. And for example, if we find a definition from the wiki, machine learning is described as the study of the computer algorithms that improve automatically through experience. So here the emphasis, the keywords are, there are some algorithms and there is some improvement, automatic improvement through experience. Then there is a definition from book Mathematics for Machine Learning, which states that the goal of machine learning is to design general purpose methodologies to extract valuable patterns from data, and ideally without domain specific expertise. And here the emphasis on extracting some patterns from the data, learning the data representation, and lack of domain specific expertise. And another definition from the deepAI.org website, which says that machine learning is a field of computer science that aims to teach computers how to learn and act without being explicitly programmed. So here the emphasis on the also on this automatic learning without being explicitly programmed. So these all definitions are sort of like if we combine them, we can retrieve some features of machine learning. So as we see, it's existence of some algorithm. The algorithm should be sort of a general purpose, and they should be able to learn through experience and without explicitly programming the rules. And machine learning nowadays used in many different fields. It can be, of course, computer science, but then just generally science like physics, biology, chemistry, bioinformatics, like medicine, also finances, and predicting how the financial market behaves, like fraud analysis, insurance claim analysis, like analysis of images or audio signals, a lot of different applications. So now when we discussed a bit about what is machine learning, we need to be able to take our real life problems that we want to solve and formulate these problems in a such way that we can use the methods available from the machine learning field. This skill of problem formulation is very important. It doesn't matter what you're doing or what you're studying. And you definitely learn this like also at school. For example, if you take like any kind of classes like math classes or physics, chemistry or biology, usually you have to extract necessary information, the most important information from your exercise, from your task, and formulate the problem in a such way that you can easily see what kind of methods you can apply to them. For example, in physics or math, usually if you have a description of a problem, then first thing what you do is you're trying to understand what you actually know already, or what is the given variables. Then you need to precisely understand what is a question, what kind of variable you are trying to find, and also what kind of relations between these variables are described in the text. And then when you formulate your problem in a such way, it makes much more easier to apply the things that you learned previously in physics and solve this problem. In a very similar way, we need to take the real life problem and we need to be able to describe it as a machine learning problem. So in this course, we suggest that machine learning problem can be decomposed into the three components, and namely data, model, or hypothesis space, and loss. Of course, there are also, it's not the only way to do it. There are different ways maybe to see the same approach, but that's how we do it at the moment. So what is the data? Well, the data is a set of collection of the data points. And the data points is a bit sort of an abstract definition. It's just some unit of information or an object that conveys the information. And the data point can be like a physical objects. It can be people, like subjects, anything you can imagine. Data points are characterized by two types of properties, the features and the labels. And usually features are the properties of data point that can be easily measured or computed, the things that you can collect like automatically. And then the label is some properties of the data point that you are interested in, you want to learn about them, but maybe you cannot collect them or infer about them very easily. And then machine learning aims at predicting the label given the features of the data point. For example, here I have some examples of data points. Let's say it's some Excel file with the numbers about the houses. It may be description of the houses, how many bedrooms are there, what is the, like, on which floor the flat is, etc., like a price of the house. Then there is some text. Well, it's just any kind of text, just a general definition. Then we have genomic sequence, image, and speech. So your task now is to suggest what are the possible features and labels for these data points. You can choose like 1 or 2 and type into the chat. For example, text file, what are the features and what are the possible labels, or the image, features, and labels. So I'll just give you some time to do that. Okay, I don't see any answers, but that's all right. I prepared some. Oh, sorry, there was just appeared one. Okay, so suggestion. For the housing data set, I assume the label is the price, and the features, numbers of bedrooms, and proximity to public transportation. Yeah, very good. Yeah, that's exactly. Size, the features, size of the building, and the label, different function of the building. Yeah, sounds reasonable. Features, location of the house or flat, and the label, price. Yeah, that's definitely. Okay, so text, features, number of words. Yes. And label, negative or positive sentiment. So it's similar to these NLP tasks. Yeah. Okay, thanks a lot. So I also prepared some suggestions. And as you can see, there are many opportunities or how you can define your features and labels, and you have a lot of freedom in that. Of course, it depends on what you are able to collect automatically. And for some types of the problem, for example, in the medicine, collecting the data in general is very hard, especially if it's something like patient data, and it takes more time to collect the data set. But for some maybe problems, it's easier to collect a lot of data. So it's really domain specific. The only things that you will need to sort of consider, or you have to have some like a common sense, or maybe also a bit of domain knowledge. You need to choose the features that are possibly connected or related to your labels. For example, if you want to predict the grade of a student, you would like to collect some features that related to the performance of a student in the school, maybe some grades for certain subjects, or some intermediate results of the exam, or something like that. And most probably you wouldn't include features like, I don't know, color of the shoes of the student, or what kind of bag the student has, because this feature is most probably not related to what kind of grade student gets, and it's just useless. So just use the common sense when you define your problem. Then in the round one notebook, you worked with the linear data set. So you had measurements from 20 athletes, some physiological measurements like weight, waist measurement and pulse, and then some exercise result like chin-ups, sit-ups, and jumps. So we formulated the machine learning problem in a certain way, but in this case, we actually can choose what are the features and what are the labels depending on what is your research question. For example, maybe I'm interested how if we can use the weight parameter to predict the exercise results. So in this case, weight going to be my features, and for example, chin-ups going to be my label. Maybe it's the opposite. Maybe I want to take the results of these exercises, chin-ups or sit-ups, and then predict some physiological parameters, weight or waist measurement. So it's solely dependent on your research question, and the only maybe assumption is that features has some kind of correlation or relation to the label. Of course, many times you don't know if the features are actually important for your predictions or classification. So in this case, of course, you can include these features with the unknown relation to the label. The next component is the hypothesis space or a model. And we define the hypothesis space as a subset of all possible maps from the feature space to the label space. So what does it actually means? I'd like to show you just to give an like a sort of hands-on example. I'd like to plot some of the these hypothesis spaces, the examples from the hypothesis spaces. So let's imagine that you assume that the relation between your feature and the label is linear, and you want to try out if this kind of equation can describe this relation. So here we have a linear predictor with the intercept equals 0. So there is no intercept. And W is the coefficient, X is a feature, and the Y is the label. So for this equation, the hypothesis space is all the linear predictor of this form. So here I used some random number as the coefficient W. So every time I run this cell, I have different kind of linear predictors that are related, are described by this equation. And I can do this infinitely many times because there are infinitely many linear predictors of this form. And all of these linear predictors, they are forming the hypothesis space for this model. So this is a hypothesis space for linear predictor without the intercept. Then maybe I'd like to make my model a bit more flexible, and I decide that my model going to be on this form. So we add the intercept. Then in this case, hypothesis space will consist of all linear predictors of this form. All of these lines are belonging to this hypothesis space. Everything that we can create with this equation. I can do more complex examples. I can add one term and get the quadratic and get the predictors of the quadratic form. And then I can go further at the cubic term. So these kind of predictors are called polynomials. So you can just add more and more and more terms infinitely many times. And this kind of hypothesis space can be represented as a nested structure because, for example, if we take this hypothesis space number 3 described by quadratic equation, if we set the W2 coefficient 0 and bias intercept 0, we will get hypothesis space number 1. And if we just set W2 0, but bias is not 0, then we will get hypothesis space H2. So all of these hypothesis spaces are infinite, but some are bigger than other. So that's why they are nested. So these kind of hypothesis spaces are related to each other. They're all polynomials. So we can also choose a completely different hypothesis space. For example, decision tree regression. We will discuss decision trees in the classification round, but briefly, how decision tree works is it splits the data in a such way that perfectly describes our data. For example, if we have one feature, which labeled here as x0, then, for example, we split our data in a such way. All the data that have x0 smaller or equal than 9 goes to the one split, and then all the others go to the another split or branch. And then we can compute the average label value or target value for this branch. And using this target value, we can also compute the mean square error for this branch. And then we can further divide this data into more splits until we build some sort of tree. So details here are not important. I just wanted you to show how this tree looks like. So here we see 3 examples of the decision trees. One, the blue line, seems to be very simple. It just like looks like something like a step function. Then there is this orange one, looks a bit more complex, and the green one has a lot of these kind of pieces that form this line. So these 3 predictors are from the hypothesis space of the decision tree regressor. And we can, again, come up with a lot of different these kind of predictors, and all of them will form the hypothesis space of this decision tree regressor. And in this case, all these functions are just piecewise function because they consist of different pieces. Here is another example for this regression problem. Here we have a multi-layer perceptron regressor. In this case, we perform the similar operation as just in a simple regression. We also compute we also multiply the weight and the feature, but then we sum up all these values and we apply some non-linear function. Details here are also just not important, just an example. But in the end, we will get something like this. So these are 3 predictors from the hypothesis space of MLP. So one of them looks like some piecewise function with 2 pieces, and these ones are a bit more complex, but all of them are just examples from this hypothesis space. And the hypothesis space is a design choice. So most of the time, you don't know which of them will work best for your problem. So you need to try many. For example, if you have some regression task, you can start with the simplest hypothesis space, some linear function. If you feel that it's not working very well, then maybe you decide to use a decision tree or some random forest, etc., etc. So this is a design choice that you have to make first. You should take into account, of course, what kind of resources you have, in the sense of computational resources, and what kind of data you have. For some data, maybe some hypothesis space is better, and for some others, so you need to try that. And in the library that we use for machine learning, Scikitlearn, you can find many models and many how to create, like the tools to create hypothesis or choose hypothesis spaces. If you visit the user guide page for Scikit-Learn, you will find here description of the linear models or linear hypothesis spaces. Then there is a support vector machine, some decision trees, ensemble methods. So in this library, you can choose your hypothesis space by choosing the appropriate model. Okay, so now let's say you chose your specific certain hypothesis space, and there are many hypotheses. You can choose between many hypotheses or many certain, let's call it certain, many predictors from this hypothesis space. So you need to be able to compare those predictors or hypotheses and choose the best one. And you need some kind of quantitative method. Of course, you can, for example, if you use a linear predictor, you can do some kind of visualization, plot your data, plot the predictor, and see which one maybe fits better. But this kind of approach do not scale well with the increasing amount of features and like a complex models. So you need some kind of quantitative measure of quality of the hypothesis or predictor. And that's what loss function exactly do. It calculates the, takes the prediction from your hypothesis and through label or ground truth and compares them. So in the round one notebook, you get familiar with the mean square error or MSE. Yeah. Then there is also mean absolute error and some other loss functions that, for example, used for classification, logistic loss, cross entropy, hinge loss, 0-1 loss. In principle, you can design your own loss function. It is possible, but because it is introductory course and we don't have very complex or very specific certain problems, we will gonna just use the loss functions that are tested and known to be useful for certain kind of problems. For the regression problem, we will use mean square errors always. And for the classification problems, we will use logistic loss or the cross entropy or hinge loss. So now we can bring all the components together and try to formulate the problem in terms of the machine learning problem. Here I'll give you some example. Given an image of a histological analysis of a tissue, how likely that the sample is cancerous or malignant tumor? So now you can write in the chat first what kind of problem is that. Is a like a regression problem or is it a classification problem? What is the data point here? What is the features? What is the labels? And if you know or can, you can also write what is the loss and what is the hypothesis space or model that you could use. So I'll just give you a few minutes. Okay, so okay, we have a lot of suggestions, and many students identified that this is a classification problem, and that the labels would be cancerous or not cancerous, or benign or malignant. Then as a feature, you can use either just the pixels of the image, or you can extract some information from these images, such as, for example, size of this, size of the tissue, edges of the tissue, some specific characteristic of this tissue. Okay, thanks a lot. Yes. Yes, that's a very good suggestion. Yes, thank you. So this is my interpretation of the problem. So, for example, I thought that the data point could be an image of the tissue sample, and then features could be, for example, pixels, label cancerous, no cancerous. Because it's a classification problem, I would maybe start with the simplest logistic regression and use the logistic loss. But of course, there is a space for creativity of how to deal with that problem. So this is it for components of machine learning, the theory. So if you have any questions, please ask. I saw one question about random forests. The question is random forest a hypothesis space? What is the relationship between model and hypothesis space? To be honest, I don't remember. I'm not sure if I can answer right now, because decision tree regressor is a hypothesis space, and it consists of the functions like of type like piecewise function. If I remember correctly, the random forest is just ensembles of different decision trees, and yes, it is a hypothesis space. Yes, I think it can be called a hypothesis space. Yes, so I would answer that random forest is a hypothesis space. And what is the relationship between model and hypothesis space? In this course, we use it interchangeably. It's the same model and the hypothesis space, but it may be used differently in different places, in different courses or books. So in this course, we use them as synonymous. Okay, so I don't see any questions about the components of machine learning. So I'll move forward then. And okay, so there is one question: when to use absolute mean absolute error instead of mean square error? Good question. To be honest, I never used mean absolute error. And I'm not sure if it's actually used that widely in machine learning. In the next notebook, you will read about sort of a middle ground between absolute error and squared error, the Huber loss. So I would guess that absolute error is not used in machine learning that much because it's not differentiable and difficult to optimize. but I can check that and maybe find some examples where it's actually more beneficial to use the mean absolute error. So I will come back to this question. So the next question, why we use mean absolute error as a metric, but loss function as but as a loss function we use mean squared error. Well, mean squared error is good because it's differentiable, and so it's a convex. And if we are talking about the combination of, for example, linear predictor plus MSE, gonna be the convex function that we can optimize. So for technical reasons, why we use absolute error as a metric? Well, I think it's just a design choice. I never used my as a error as a metrics, but maybe it's dependent on the field. If you have some research papers that use my as a metrics and you want to compare your results, you would also use the same metrics. But I don't see the specific reason why you would prefer my as a metric. Well, it's just easier to interpret. It's just the difference between the true label and the prediction. In that sense, maybe it's more interpretable than the square error, but otherwise I don't see any other reasons. Yes, so one of the students commented that the absolute error is sometimes used as a way to measure the accuracy of an already trained model. That, well, might be true. I cannot comment on that. How can we identify what features are relevant to predict a specific label? Well, first of all, common sense. If the feature is definitely seems like it's not gonna, like with the example of the predicting the student's grade, like it's just a common sense. Then you could use some knowledge from like feature importance. There are certain methods that you can employ, for example, and see if the features is really adding in any information or not. In Scikit-Learn, there are some tools to sort of rate features or do this feature important analysis. It's not always reliable, and it depends what kind of model you use and what kind of data. But in majority cases, first common sense, then maybe do visual analysis of your data, like, I don't know, simple plotting features against the label, some exploratory data analysis to just get rid of some really useless features. Some methods like dimensionality reduction, if you have a lot of features and you don't know which one, like you think that there are too many of them, you could use some dimensionality reduction methods that we will also learn at the end of the course. Okay, so now I will move to one topic that I wanted to briefly discuss with you, and this is about the Python classes. Why I want to discuss it? Because a lot of like, I would say even all methods that we use from this Scikit-Learn, they are like examples of the Python classes. So I just wanted to give you an example. What are those, to understand what are these attributes and methods you're going to be using when you use this Scikit-Learn regression or classification machine learning methods. So I took example from this tutorial. And if you want to understand the details or know it more thoroughly, you can check this tutorial. It's quite nice introduction. So Python is the object-oriented programming language, which basically means that everything is constructed or designed around this concept of object. For example, you're already familiar with the NumPy arrays, and here there's example of NumPy array. And NumPy array is an object of a class NumPy, and you can get all the methods and attributes or features of that object by using the this dir function or dir keyword. For example, here you can find this attribute shape that will print the shape of the array, and then there is a method squeeze that will alter the dimension of the NumPy arrays. So what is the Python classes? And if we take the definitions from the Python documents, it is a classes provides a means of building the data and functionality together, and creating a new class creates a new type of object, allowing new instances of that type to be made. It might be sounding a bit cryptic or not understandable if you're not from the programming background. So maybe better to illustrate with an example. And here we'll have an example of class employee. And the object of this class will have attributes or properties or characteristics, such as first name, last name, pay, email, and we will be able to apply these two methods to the object from the employee class. And the methods are get full name and pay rise. So each object is sort of representing each employee, and each employee is characterized by attributes, and we also can apply some methods to this object. So normally how we construct a new class, we start with this keyword class. And then here we define some variable that we're going to use later on. And here we have some strange methods that call init, and also strange variable that called self. At this moment, it doesn't really matter. It's kind of, I just want to illustrate what are the attributes and what are the methods, but just briefly, this self, it's a kind of representation of the object itself. And when we are constructing this class, we have to explicitly define it. And then init methods is a so-called construct in Python. And when we will be calling our employee class, then Python will create an object, this self, and will pass it to this init method with the other parameters. It doesn't really, like, if you don't understand, it's okay. It's not the point here. You don't have to write the classes yourself. You're gonna just use them. So I wanted to show you what are the attributes. So here we define the attributes, and we will have the attributes first name, last name, pay that we will provide to this class, to this init function. And then we'll create a new attribute, the email. And then we'll define some custom functions like a full name and apply rates. The full name will return the full name of the employee, and the apply raise will calculate the new salary for the employee after the raise. So when we call this class employee, we have to provide certain parameters like a first name, last name, and pay. So I provided it here. The first name is test user, and this is the pay. And this line of code usually referred to as instantiate a class or create an instance of a class or create an object of a class. So here we're creating the object of this employee class. Then we can also print out with this do method the attributes and the methods for this class. And as you can see, this is the attributes that we define by ourselves. And those are the methods that we define. And also, this is a variable that we define. We can print the attributes of the object by using object dot and some attribute, for example, object dot first, object dot last, etc. And it will return us all of these characteristics or properties. And then we also can apply methods, for example, object dot methods, and also don't forget the parentheses. For example, here we applied the raise, and the current pay and the new pay is going to be raised from 50,000 to 52,000. And here we also create this full name. So this is very simplistic example of the Python class. And if you check the Scikit-Learn documentation for the linear regression that you used in your notebook, you will see that this Scikit-Learn linear model, linear regressions is also a class. Here you have the parameters of the class. So you need to provide these parameters when you call linear regression. And if you check the source code, you can see that this class is defined in a kind of similar way as this simple employee class. It's just more sort of complex, more advanced. We also use this keyword class. The same way we have these init methods, and also here we set the attributes. And we also, in the same way, write the specific methods that could be applied to the object of that class. And this page is a very typical example of how these docs for all of these machine learning models in Scikit-Learn looks like. First, you have the name of this class, then you have some parameters, then you have some short description of this model, and more detailed description of parameters. For example, you're already familiar with the fit intercept, and here you can see that this is a Boolean, so you only can provide true or false, nothing else, and that the default value is true. For example, if you want to build a linear predictor without intercept, then you have to provide the fit intercept false. But if you want to create a linear predictor with intercept, you actually can skip defining this parameter because by default it's true. Then we have a list of attributes that you can access by doing like object.coef, object.rank, and etc. With this attribute, you're already familiar, the coefficient or weight. And in round one, your task was to find how to retrieve the value of the intercept. And actually, it's object.intercept and the underscore. You also have usually some short example of how to use this kind of machine learning model. And if you want to copy paste it, you can click this hide prompts and outputs and just copy paste the code and try out in your notebook. Then we have description of the methods. I believe you used fit method and predict method. And in this description, you find what kind of parameters you need to pass to this function. And also, importantly, what are the format of these inputs? For example, here we can see that the feature matrix should be of shape number of samples and number of features, but labels, for example, could be just number of samples or number of samples, number of targets. And then what this method is return you is just a fitted estimator or fitted model. So then you have a description of all of these methods and some more examples in a different context that you can also check if you are interested. So this is a very typical description of the model. And if you, for example, forgot how to use certain model, you can just Google, open this page and find all the information you need. Or for example, here I have some example of this linear regression, where I called the linear regression class and passed some parameters. And here it says to me that it's an object of this linear regression. And for example, I can use tab autocomplete and browse through the attributes of this object. Or if I want to have a full list, I can go and just use this dir function. And then I have all the attributes and all the function. So just to mention a few common errors when you use the Python classes, especially in this round one. If you're copy pasting, for example, people often copy paste this regconf or regfit. Be sure that you, when you building your second model with the intercept, that you actually put the correct name of the model, something like that. Otherwise, you will fit a different model and you will get different result. Another mistake is overwriting the class name. For example, do not call your model with the same name as the name of the class, because you will overwrite it, or you can just mess up with that. And in general, you will notice, as long as we are learning the new models from Scikit-Learn, that you will have to do the same steps for all these Scikit-Learn models. First, you have to import models from Scikit-Learn. Then you create an object of that certain class. It doesn't matter what kind of model is that, decision tree, linear regressor, some classifier, doesn't matter. Then you just use fit methods to fit your data and .predict to get the prediction. So after a few times, you will be able to do this fitting and predicting even without looking to the documentation and reading, because it's very simple and it's very general. Okay, so that is it from my part. So if you have any questions, please ask now. So in the next round, we will be continuing to work with the regression, with the linear regression and few variation of the linear regression model. We have a question: why in the definition of machine learning it is mentioned without explicitly programming? We use, could you please abbreviate LSE? Please. What does LSE mean? Least square error, yeah. We use least square error, which has an explicit, mean square error, which has an explicit formula, and we are telling it what to do clearly in prediction regression problem, right? Good question. So your question is where the automation here? So first of all, as there was some already discussion in chat about the linear regression, because you could, for example, use the normal equation to solve it. Then you can use, for example, gradient descent. We are so the comment, the question from the student continues. We are telling what to do, and this is explicit. The machine is not discovering a method itself. Well, I believe that automation here, in the sense of that you just throw all your data, a bunch of your data, to a machine learning algorithm, and it's just sort of throws out the results and acts as a sort of a black box. The contrast is usually explained as previously you will have to design your features before you apply any kind of methods. So you cannot just take your data and apply some certain algorithm. First, you need to, as a domain expert, you need to do the feature engineering. You need to select the features, you need to transform the features. And after doing this manual work, you can apply the certain statistical methods or some sort of algorithm. In contrast, in machine learning, we have few rules. Of course, it's not like a 100% automated process. You cannot just open the computer and says, this is my data, give me the result. You have to set some rules. And the rules that we have to set is, first, we have to restrict the hypothesis space. We need to choose what kind of predictors we want to have. We need to define how we measure the quality of the hypothesis space and what kind of algorithm we use to sort of find the best model. So it's not 100% automated, but it's much less. It has much like a less amount of manual work or manual feature engineering than, for example, some other methods. So it depends on what do you think, what is your expectation of the automation process? I will think about that, and maybe I will come up with the better answer. If I come up with a better answer, I will post it on the slide. Would you please open round 1 to Python notebook and explain a bit about it? I would as I said already in the previous sessions, I'm not going to step by step through the notebooks. We assume that going through the notebook and reading the text, the theory, and doing exercise, you would do it independently. Usually, if you have any specific question, you can ask them in advance or here maybe, and then I can comment on these questions. So do you have any specific things that you don't understand that we can discuss? Another question is, I saved the first notebook with different name. You have to keep the original name. Unfortunately, the system that we're using, it searches your submissions according to the original name. I have a sort of template, and the name and the structure of notebook, the metadata should be the same. Otherwise, I won't be able to collect your notebook. Okay, so the question is how to open the Python notebook, submitting and running the notebook. I would refer here to the recording of this introductory session that we had. We discussed these issues like last time, so I just don't want to repeat it again. And also there are instructions on my courses, so you can find detailed instructions there. But if you weren't able to do it, or you will have some problems, you can just email me or write on Slack so I can guide you if you won't find how to do that. Okay, if there are no more questions, then just a reminder, the deadline is on Monday, midnight. And the next book gonna be released also on Monday, somewhere before the noon. Okay, so then thanks for attending, and have a great weekend.